Welcome to a mind-bending journey deeper into Higgs boson. Oh yeah, oh yeah! I am Jennifer, your host. Let's this cold brew news series begin now. The heart of the quantum realm, where the rules of the universe take a captivating twist. Today, we're delving deep into the intricate world of quantum mechanics, a fundamental theory that has redefined our understanding of reality. Scientists working in labs, equations scribbled on whiteboards. As quantum systems interact, the result can be the creation of quantum entanglement, is a fundamental phenomenon in quantum mechanics that can occur between any two particles, including those involved in the decay of the Higgs boson. Quantum mechanics isn't just a theory, it's a revolution that shattered the boundaries of classical physics. It's the secret language of the subatomic, the symphony of particles and waves. Montage of particle collisions, wave interference patterns. Picture this: classical mechanics, the reigning theory before quantum mechanics burst onto the scene, describes the motion of everyday objects. But when we zoom in, oh, the surprises that await! Transition from a spinning top to a zoomed-in particle. Chaos theory, a mesmerizing facet of classical mechanics, dances on the edge of predictability, paving the way for quantum mechanics to take the stage. Visual representation of chaos theory equations. Now, let's unravel the enigma that is quantum mechanics. At its core, it's a fundamental description of the physical properties of nature itself. But what is nature? It's the very essence of our universe, from the smallest atoms to the grand expanse of galaxies. Montage of natural landscapes, galaxies, atoms. Yet, in the quantum realm, the rules we've come to know and love can become as elusive as stardust. Meet the atom, our cosmic building block, composed of electrons, protons, and neutrons. Their properties become so intertwined that a description of the whole solely in terms of the individual parts is no longer possible. Erwin Schrödinger called entanglement, the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Quantum entanglement enables the counterintuitive properties of quantum pseudo-telepathy, to achieve higher expected payoffs and equilibrium than can be achieved in any mixed strategy Nash equilibrium of the same game by players without access to the entangled quantum system. It is a real-world phenomenon that has been experimentally verified and has implications for the design of cooperative games, and can be a valuable resource in communication protocols, such as quantum key distribution, and that allows for secure distribution of cryptographic keys, while the Higgs boson is a fundamental particle in particle physics that was discovered at the LHC. To deepen our understanding of the fundamental forces in particles in the universe. Superdense coding. In quantum communication, and is often used as a building block for more complex quantum communication protocols, such as quantum teleportation. It has been demonstrated experimentally in various quantum systems, including photons and superconducting qubits, that allows for efficient transmission of classical information using fewer qubits. The Higgs boson, on the other hand, is a fundamental particle in particle physics that was discovered at the LHC. While both concepts are related to quantum physics, they are distinct and unrelated to each other. Atom components. Electrons, those elusive dancers, flit around the nucleus like fireflies in the night. Protons and neutrons, the steadfast companions, form the nucleus at the heart of the atom. Electrons orbiting a nucleus. Quantum mechanics unravels this cosmic choreography, revealing that particles and waves aren't just separate entities, they're both and neither at the same time. Showing particle-wave duality. But here's the twist that'll leave you in awe: the uncertainty principle. Brace yourself for a roller coaster of probabilities, where the more we know about one aspect, the less we can predict about the other. Illustrating uncertainty principle. Now, let's peer into the mesmerizing double-slit experiment, a tale of light that unfolds as both waves and particles. Double-slit experiment setup. As light passes through two slits, it creates an interference pattern, reminiscent of ripples in a pond. But watch closely, for when observed, it transforms into individual particles hitting the screen. Pattern and particle hits. It's like watching a cosmic dance of transformation, a reminder that reality is as malleable as clay in the hands of a cosmic sculptor. And as if that weren't mind-boggling enough, let's journey to the land of quantum tunneling. Imagine particles boldly crossing barriers they seemingly shouldn't be able to breach. SNIR doesn't permit conveying messages quicker than light, as exhibited by the exceptional hypothesis of relativity. The no correspondence hypothesis guarantees noticed connections are factual, and entrapment permits testing for buried factors to repeat the relationships anticipated by quantum mechanics. Particles tunneling through a barrier. This is where the ordinary collides with the extraordinary, particles defying classical physics, opening doors to radioactive decay, nuclear fusion, and even scanning tunneling microscopy. Nuclear fusion, tunneling microscopy. Now, let's dive into the captivating realm of quantum entanglement. Imagine particles becoming intertwined, their destinies forever linked, challenging our very notions of individuality. Hypothetical properties more fundamental than the quantities addressed in quantum theory itself, knowledge of which would allow more exact predictions than quantum theory can provide. A collection of results, most significantly the Bell inequality in physics, states that quantum mechanics is incompatible with local hidden variable theories due to measurement assumptions. This inequality was introduced by John Stuart Bell in 1964 and has been developed through Bell-type inequalities. Advanced tests consistently show that physical systems obey quantum mechanics, making the results incompatible with any local hidden variable theory. Entangled particles. But hold on to your hats, because entanglement doesn't mean faster than light communication. It's a cosmic conversation that transcends distance, revealing a hidden symphony in the fabric of spacetime. Showing entangled particles communicating. As we wrap up this whirlwind tour, remember, quantum mechanics isn't just a theory, it's an exploration of the very essence of existence. It's a dance between particles and waves, a symphony of uncertainty, and a cosmic invitation to expand our understanding of reality itself. Have demonstrated that broad classes of such hidden variable theories are in fact incompatible with quantum physics. According to Bell's theorem, if nature actually operates in accord with any theory of local hidden variables, then the results of the Bell test, named after John Stuart Bell, is a real-world physics experiment that tests quantum mechanics' local realism theory. It determines if the real world satisfies local realism, requiring additional variables for particle behavior. Bell tests are used in physics laboratories and quantum cryptography protocols to detect spy presence. So, join me on this adventure into the quantum realm, where contradictions become catalysts for discovery and where the mysteries of the universe unfold one paradox at a time.